Magnetic fields can be used to confine electric charges in motion to certain regions of space through two primary mechanisms. First, magnetic charges tend to spiral around magnetic field lines, and the net travel of the charge tends to be along those field lines. Second, in a region where magnetic field lines are converging, there will be a component of magnetic force away from that region. This produces an effective magnetic mirror, which sends the charges spiraling back from whence they came. A simple magnetic bottle can be produced by two magnetic dipoles, shown here as two coils. The electric charges can be trapped in the region between these two coils. A toroidal magnetic field can also trap charges by keeping the charges spiraling around the magnetic field lines. This is a simplified version of confinement used in plasma and nuclear fusion research projects like the International Thermonuclear Experimental Reactor. The Earth's dipole magnetic field can also provide a magnetic trap for electric charge. The charges spiral around the magnetic field lines, traveling north and south. The convergence of the magnetic field lines at the poles serves as magnetic mirrors. The net result is that the charges tend to be trapped in a band around the Earth, forming the Van Allen radiation belts. Let's examine the motion of an electric charge in a uniform magnetic field. Because the magnetic force depends upon the cross product of the charge velocity and the magnetic field, the motion is usually three-dimensional. We will start with the special case where the initial motion is perpendicular to the magnetic field. In this case, the resulting motion will only be two-dimensional. Since the force, and hence the acceleration, is always perpendicular to the velocity of the charge, the resulting motion of the charge will be circular. The force on a negative charge will be reversed compared to a positive charge with the same velocity. As a result, positive and negative charges will traverse their circles in opposite directions. Speed also affects the radius of circular motion. However, the time it takes is not affected by the speed. The frequency of orbits only depends upon the charge, the magnetic field strength, and the charge's mass. Returning to the more general 3D case, the net motion of the charges will be determined by the parallel and perpendicular components of the charge velocity relative to the magnetic field. The component of velocity parallel to the magnetic field determines the part of the motion along the magnetic field lines. This part of the motion is at a constant velocity. The component of velocity perpendicular to the magnetic field lines determines the circular motion around the magnetic field lines. The net result of these two motions is a helical motion, where the charges spiral around the magnetic field lines.